Record on the computer. Don't worry about it. That's cute. Yeah, I could hear all of you studying. It was cute. I'll tell Andrea. I'll have to phone her and tell her. You know what they were all doing? um, so if we've got, if you think about quantitative versus qualitative, and I said this in the beginning, that idea of you've got the quantity, right? Quantitative and qualitative, okay, quality. So the difference between the two. Up till now, we've done, for the most part, qualitative methods. Surveying fits well in quantitative. Um, Quantitative is you're using a lot of quantity, a large quantity, of many of them. So that's the idea. You've got lots of data from lots of sources, and you pile it all in and do this comparison. But as he says here, right, it's like knowing algebra. You can use the very same statistics and argue two sides of the same argument sometimes, because it's just the way you interpret them. So think about this here. School shootings, right? Epidemic of violence. Well, it's an epidemic, but if you think about how many school shootings they've had, there's not that many. And when you look at it as statistic, there's not very many. But when you think about a bunch of school children being shot, well, this isn't shooting, yeah, school shootings. If you're looking at children being shot, if it's the last one that happened, if you've got a few children that have been shot, it's horrible. So it would feel like an epidemic, even though it's a very small statistic. So qualitatively, you're relying on the issues around it, we'd say it's a big deal. Quantitative would have to dismiss it somewhat and say, well, it doesn't happen very often. So how much resource or how much money should we put into it? And at the back end of research, often that's what it's about, is what resources get put into work or things that have been, research has been done on. So child abuse has doubled every year since 1950. Doubled from what? If it's 1 in 1950, it's 2 in 51, it's 4 in 52. If it's 1,050, then that's proportionally much, much higher. So you've got this notion of it's a relative statement to say whether it's every year, where did it start? Those curves look like this versus this if they're doubling every year, depending on where they start. Binge drinking, you're all gone the way to alcoholics, right? You can beat the casino. Therein, when you look at casinos all the time, in casinos, everybody goes there. They make billions of dollars because everybody thinks they can win, and they don't. The statistic says it doesn't work out. So, but they try to play, which is interesting. They try to play statistics to get to win, and it doesn't always work in your favor. We'll come back to that in a second. So for now, you get things that go into statistics. Dark figure of crime. In criminology, you see that. They have no idea what the impact is of crime that's unreported. You only know what's reported. What got reported to the police? Well, if people don't call the police and tell them, then there's crime, but nobody knows about it, except the people living there. Or the other is, the other one that sort of confers to that is police driving around at night. They said, do studies and see what the effect of police. I remember one mayor a long time ago saying the police shouldn't be driving around all night. It's counterproductive, it's expensive, and they could use some sleep. Let them be like firefighters. Sleep in the police station, call them out when you need them. And people said, no. It's the idea in that law enforcement model is crime prevention. But there's no statistic that shows it works. There's no statistic that shows when the police drove by and somebody didn't commit a crime. So you got to look at who's defending the numbers or attacking the numbers. What's the perspective? Where are they coming from? What's their motive for it? And often you look at financial or politics and say, oh, this is good for you to say this. What's being asked, who's asking what, and that's really where we get to the method, this part here. What's being asked, how's it being asked, who's asking it. You're starting to shake it down and say what's underneath there. Now, I talked about this a little bit in the beginning, constants, the thing that stays the same. That's the thing in your group that doesn't change. Your constant is if it's your student body you're doing interviews with or surveys with, that's a constant. It's the student body at Guelph Humber. The variables become male, female, age, what year you're in, whatever identifiers, and demographics do that for us. That's why they ask you questions in surveys. If you remember back to that week, in surveys they ask you, where do you live, what's your postcode, how much money do you make, how old are you, what's your ethnic background, what's your religion, all of those sorts of things. They put them in a statistical system process. They put them into the system, and then they have the computer generate relationships between different variables and see, does this one correlate with that one? Does this one cause that one? And that's the big deal. Causality is the big deal with variables. That is the thing. And if we were doing this on the test, this would be an important one. Hang on a minute. I touched the button. There we go. It would be a big deal to get at causality. This is what you're going to get to next year. You're going to show that changing this variable affects that variable. It's not as simple as they are correlated. Okay, so what, they're correlated? It's that and that's where we use the independent variable and the dependent variable. If you alter the independent variable, does then the dependent variable change? So you measure this one, and you'll hear that measuring. Which one do you measure? Which one do you adjust or do something to? You modify the independent and see if it changes the dependent. If you change the parents, they have different kids. So that's the causality and with variables, what you're looking at. So then you get to some of the other things you're going to see in stats. So when you think about this graphs, what you see with a graph. So this one, when you look at it here, in this graph, there's something, I hope that in that quick graph you say, wow, there's something out of whack on that third quarter. I don't know if any of you ever would look at graphs or pictures or pie charts, and there's that sort of looking at it saying, what do I do with that? So what's the dependent variable? What's the x-axis, the y-axis? The x is independent, y is dependent. Those are terms you'll have to know. Next year, you'll learn them as you go, but they start to become important. But what you've got is, as a blink, and you think about this like a Snapchat. You look at it for 20 seconds and you leave. You look at this one for 20 seconds, what do you see on the one over here on the left? Ideally, I'll answer that myself because there's only 4 of you. Ideally, this one sticks out for you. So what it draws to your mind is, what caused that? What's going on? And it is the cause. What's the issue? So that's which variable should we interfere with to try and figure that out? Why are males in the third quarter way up here and females have stayed relatively the same? So what is that about? And who knows what that is, but it's the idea that I want you to look at when you look at a graph, say, oh, okay, that's what's going on. This is a bell curve. It's an upside down bell. That's what it's about, right? It's a bell. So laws of chance come in. We'll look at chance in a minute. Statistical inference, this is what we try to do. You look at the statistics and all those numbers, and from it, you draw this conclusion that sort of says, it seems like this. If it's really strong, if the correlations are really strong and you can show causality, then you'll make a statistical conclusion. But that's sort of the language of stats. Now these terms you need to know. They are key throughout statistics. The mean, find a way to remember these words that works for you. I remember the mean because it's average. I don't like averages. I like the median. I don't like the mean. And I'll show you why. So mean is easy to remember because it's average, and I don't like averages. Mode, I don't know, a la mode, it stands by itself. It's how many times does this number show up? That's all it is. It's a counting thing. I'll come back to these. And the median is this middle case. So when you put everything in a row, you pick one out of the middle. It's as simple as that. You pick it out of the middle. You've got a bunch of dots. That didn't work. Bunch of dots all in a row. Text. They're just there. Just all those dots. The median is just the one right in the middle. You count them to the middle point. Whereas the average weighs them in, and all of you know how to do an average, right? You add up all the numbers, you divide. So think about this. So here's an average one. Look at this company here. So the total income is $10 million a year for the company. There's 100 employees. So the average income is 103,000. So if you go to McDonald's, the average income might be 103,000, might be 100,000. What do most people at McDonald's make? What do you think? Are they making 100,000? $10 an hour, $11.75, whatever, minimum wage. So when you break it down in this company, and we do that at McDonald's, everybody's making $11.75. The supervisor makes 15, the manager makes 25, or assistant manager makes 30. Like you go up, and the owner makes, and that's what this looks like. The McDonald's, it's $10, it's $11 an hour, right? So most people are making that. If you put them all in a row, you've got $10, $10, $10, $10, $10, $10, and then you've got 20 and 25, and then a million. Well, 10's the one in the middle. If you go for a job at McDonald's, you're not going to make the average income of 100,000 a year. If you go for a job at McDonald's, you're going to make what most people make. You're going to make 40,000 a year, because that's what most are making. The bulk of people, the number in the middle has a better reflection of when you put everybody together and just where am I going to be in. So the trouble with average is it takes out this big number comes in. Oops, this big number comes in, and this big number is called an outlier. It's the really odd one. Most of the numbers are packed in that range of 90 down to 9, but this big one here is an outlier. It is it's the one that you look at and say, what's going on with that? Right here. It's odd. It stands out way by itself. So the median is the middle one. The mode, because everybody's making 40, almost, most of the people here are making 40,000. The mode is also 40,000. It's just the number that shows up the most. The median, it might be like for us at McDonald's, it's 11.75. But if you've been there a year, you've got a 25-cent raise, so it's 12, and it's 11.75 and 12 and 12.50 and 12. So you've got all those numbers all in that range, and the median's going to still pick out. That's how much money you'd make. You'd make 11 to $15 kind of thing. But when you do the average, it takes the boss in. Now it's altered it. So if we look at, I'll show you on our website here. What am I looking for? Maybe it's here. Just a sec. No, it's not John Lee Hooker. It's this one we want to look at. Just a sec. Can you see that? Can you see the course website? Yes? No? Probably not. We'll take that as a no. Find a new share. There it is there. Okay. Now can you see the course website?
Yeah.
Okay. So let's look at grades on a quiz. This is how these numbers start to work in. We can do the midterm. Give me a second here. So there's our numbers, and stats will always show this up. We've got the average grade of 67%. With a standard deviation, there isn't one. It means it's all very close. So it didn't get worked out. Now you can work through the names and see where they stand. Let me pull up another one. Let me pull up a quiz. Just a sec. I'm going to turn this off so the names don't pop up. Uh-oh. Touch the button. Give me a sec. Mm-hmm. Let's see if this will give us a standard deviation. I may not have asked for it, and I didn't ask for it, so I didn't get it. Okay, just a sec. I got to go back to last year. What have we got? Summer. I want winter. Just a sec. There we go. Winter. 2015. This will work. It's a bit slow. Actually, I'll let it run in the background while I do the other stuff, so you don't have to sit and wait. So when you move to these, here's where they look on a small scale. The average, right? You add all those numbers up, and then when you break them down, they turn into an average of 12. You add them up, divide them by 5, you get 12. So that's how it kind of works. But that's typical average. Yes, good, no, good, bad. Oh, I know what I can do. Oh, I know why I did that wrong. I needed to do grades. Oops. So if you go to the next here, you go to the next then slide. The median is just the number in the middle. So you've taken all of these numbers, 3, 5, 7, 7, 38, put them in a row, median, one in the middle. It's just what number's in the middle. Now, if you looked at this and said, so say I was watching people coming into the room and saying, I wonder how often they look and find a friend before they sit down. So if that's what I'm thinking, what I would get then is this, 1 week I watch, I get 3 people. The next week I watch, I get 5. The next week I watch, I get 7. Then I get 38. Then I get 7. I take my term together. Say on average. So typically, if every week, if that's what you saw every week, on week 6, how many people would you expect to see sort of nodding or finding a friend before they sit down? Would you be expecting to see the average, which is 12? Or would you be thinking, no, it's going to be more like down in this range, more like the middle? And that's the value of the median. It gives you that idea of, it's more like, oh, that's really what we can expect. What's the 38 here do for us? What do you think happened there? So if that's, let's just say that's our standard class and people coming in. What do you think we are looking at there for a reason? Any thoughts on why we might be getting 38? How about more people showed up? Simple as that. There's a test that day, so people showed up. It could be only just that simple. It may be nothing more than that. And that's the stuff that you sort of look at and say, oh, where do we stand? So if you look at, that's an outlier, the 38. So if you look at kids, they do some research on kids watching TV. How much TV do they watch in a month? So most kids, they watch them, they pay attention, they ask their parents. Most kids are 3 hours, 5 hours. It varies. But then you've got some kid that's 200. Again, in quant, if you just go with your average, you've got an average of 45 hours a week. Well, that doesn't really work. And this is where the qualitative quantitative is nice, because if you think qualitatively, you say, what happened when that, why is that 1 week so weird? And you would say, oh, you know what, the kid's got a broken leg, or that month. Some kid's got a broken leg. What do? They play video games, they watch TV. So it's accounted for. Whereas if you just go with stats and go with an average, I think you're in trouble. So you get this thing called the distribution. It's how far, and that's where you start to figure what's the middle point of everything. And then how far is everything from that midpoint? So and you do think about it just as midpoint, how far either way. That's the idea of a distribution. So here, if we look at your grades, let me pull this one up. New share. Here's some grades from a class. So the maximum grade, you can see that the maximum is 87, average of 66. Somebody's doing 45 in there, right? So you've got some variation. The median is 65. So that means the middle grade, the middle score for people was 65, right? If you look here, that's this one. That's the middle point. And the average is just a little higher. It's been pulled up a bit. But that's because you've got a really high grade. Or what you've probably got is a bunch of people up in here. So you've got a few really high grades to pull it up, and all the rest are sort of bulked in here. This thing here is a standard deviation, the 8.86. Standard deviation is how far are things from the, and it is back to the average, but in that average place, how far are the grades out of whack on that? If the standard deviation is 12, that means most of the people's grades are within 10 points. So let me show you one here with this. Back to this screen here. If you do, I don't know if I can insert text. No, never mind, I'll go with this one. Annotate. Okay. So if let's say our midpoint, we're worried about our, call it 70%. Yeah, let's call it 70. Yeah, let's call it 70%. So your average is 70%. One standard deviation, and if my standard deviation is 10, or call it 10, what it means is most of the grades are within 10 points of this 70. So if 70 is the average, and most of the grades are within 10 points, where are they? Because it doesn't matter which side they're on. They could be down or up. So where are most of the grades? In your head, what do you think? Tell me if I'm right. Most of the grades are between 60 and 80. Make sense? You can type away for me on that. Yes, no? So you're on either side of 70 by 10 points. Yeah? If you go to 2 standard deviations, then it means you're within 20 points either side. So at this, when you look at frequency, that's actually how many people are in the room. So in that last one, we would say how many people were in the class, the actual frequency. But then when you do average, you're doing a different sense. It's relative out to 100. So the actual number of students is 87, but out of 100, the numbers start to shift. So you need to understand the difference between frequency and distribution. So let's go another step. So this one is a bell curve. It means that the median, the mean, and the mode, those 3 numbers are all in the middle. They all are the same number. You don't see it very often. When they talk about bell curving your grades, you don't want them to bell curve your grades, because what that typically means is the low grades get pulled up and the top grades get pulled down, because they're trying to make it look like this shape instead of leaving it alone and looking like this shape. This one is not a bell curve. So to bell curve this, you would pull some of these up. You would do this. You'd want it to go up and down. So you'd adjust here and here. So I don't like it. It's better if you've got a problem with our grading system, than what we do is up the grades for everybody. You don't bell curve them. You just increase. So if you've got a distribution like this, this is more like what we saw. What we just saw on that last screen looks more like this. The mode says here's the number that showed off the most, but this one is what's the number in the middle, and the average was below that. What caused the average to come down? Is it because there's a lot of grades jammed in here, or is it there's one outlier? And that's what you start to ask and look for, and that's where the stats become meaningful. So the interpretation, and you don't need to worry about interpreting, but if you've got that, understand that piece, you start to shake out this raw stat on a on even just a grade and say, What does that mean? My median is 65, mode is 70. So more people got 70 than any other grade. The median, the not grade in the middle is 65, but the average is 66. So it's here. So I got a whole bunch way up here that pulled the grade up, that pulled the average upwards. And there's no way down. If we had one way down here, one outlier way down here, it would pull the average way down. So we're fairly well lumped together. That's not bad. So given this is the midpoint, most, or the average of 66, most grades are within, each one of these lines represents 5. Most of the grades are here between these two. And if you go out from, instead of going out 10, you go out 2 standard deviations, you go out 20, almost all the grades are here. And if you go 3, you capture essentially everybody. We'll come back to that in a sec. But so there's a value, there's a reason for doing those analyses and pulling out those numbers. They're not just, they're actually meaningful to people. Now, correlations are this: positive, they move up together, positive correlation. They move negatively. They've got a correlation, but it goes back for, instead of 15. If this is, say, maybe this is your income and age. As you get older, your income is less playing a sport. But as a mathematician, maybe you start here, but your increase, as you get older, your income goes up. And then this is, there is no correlation. So correlation is positive or negative, or none. Correlations are interesting because when you look at a correlation, there's correlations that have nothing to do with anything. If we do, well, let me just pull up a search here. Correlations, spurious. You see the term spurious correlations in the book. It's not the one I want to do. Oh, slow. Oh yeah, here we go. Oops. So new share. Right, here we go. Suicides by hanging, strangulation, and suffocation. And how relative that is to how much money they spent on science and space technology, right? Oh, look, they go the same. They must be correlated. Well, there is a correlation. They have nothing to do with each other. People who drown by falling into a pool and films that Nicolas Cage appeared in. Wow. There's that thing that you look at, holy mackerel. They have no correlation. They happen to move along together, but they're not connected. There's no causal relationship. And that's why cause matters. Correlation is, they happen to be going along at the same time. We're traveling on the bus together. Cause is, I'm on the bus because you told me how to get on the bus and you're showing me how to get to school. There's a correlation thing. Some other language you're going to see that comes up. You think about this stuff. Whiskers. When you see language in quant and you're not sure what it is, think about it in terms of other language. You know, when they talk about quartile, that means they've divided into 4 parts. It's the first quarter, second quarter, third quarter, fourth quarter. Well, you might be only doing the Q1, 2, 3. It's you're doing what's in the middle, but it's split into 4 equal parts, 4 quarters, right? 4 quarters is $1. If you go to whiskers, you see the term whiskers. Whiskers, cats, whiskers, mice, they have whiskers. It's so that when they try to go through a hole, if their whiskers are rubbing on the edge, it means their body won't fit. So they got to think of, there is that, can I go through or not? Whiskers are on a plot. They're the edge bits. They're sort of hangers out. They're not quite outliers. They're not extreme, but they're sort of on the edge. So when you see that language, put it in perspective. Don't let it get overwhelmed by it. Oh no, I don't know what that is, and it's that. It's the same kind of language used elsewhere. So standard deviation, you're not doing it. I'm not going to have you do it, but it's, if you think about it, this is the process for doing. Now what you do is load it into Excel, and that's what you'll learn next year. You load your numbers in, and you get Excel to do a standard deviation for you. What you get at in that, though, is it's got this whole squaring things in and out. And, why does it matter, standard deviation? So let's look at this. If you've got here, we do a bunch of people on the quiz, they get 48% on the exam, right? Or 48 out of 50. Or out of 100. So the average, if you look here, 48, 48, 48. The average is 48, right? Because there's no variation. But here, you add them up and divide them by 2, 4, 6, 7. It still gets you the same average. So this X with a bar over it, that means average. So it gets the same average either way. But look at the chart. And this is again back to looking at a chart. What you see in there is the red line for group A. They're all the same. Group B is spread out. What's the variation, the deviation from the middle, from the average, not the middle, the average? What's the deviation? But what's the deviation that's really current? What's like the most likely? Not all deviation. So we start to do this. So in it, there's this process. You can skip this slide. This slide is about doing squaring and unsquaring and why you do that. This is important though. If you look at one standard deviation, what you would get is this grouping of stuff. Let me just make this slide big. One standard deviation gets you here. So you'd have the three numbers, because this is more or less a bell curve. So your mean, your mode, and your average are all in the middle. So let's call it 70. One standard deviation, so 68%, and this is where 68%, if you think about that as a group, out of 168, the language of that, is most an appropriate word for that? At 68%, majority is in like voting in that is only one more than the other side. So 68% is 2/3. It's most of the people. Most of the numbers fall within that. One standard deviation here captures most of the data. If I watched you coming in the class, most people look, out of 100 students, most people looked at. This is how many. So it gives you that sense of, this is a really good idea of how many. A two standard deviation. So the standard deviation is a number that is worked out mathematically. Your system does it. If it says it's 5, here back to I add in, if we make this 70, then at one standard deviation, most of the grades are between 60 and 80, because the standard deviation equals 10. Are you with me on that? So the computer calculates this for you and says, ooh, standard deviation is 10. Hang on a minute. Not plus. Standard deviation equals 10. So given that it's 10, if you go to 2 standard deviations, you're now at, so see this lines up here, right? At 2 standard deviations, it's 10 times 2 is 20. So it means 20 points either way, which is 50 and 90. That captures, and if you think about this number, it captures most, I would say. It's coming, just a sec. Slow. 95% are captured in 2 standard deviations. So if you think about 95% of the class do this, that means most. So I would go with this is almost all. Most is here. 1 standard deviation captures most of your data. 2 standard deviations captures almost all of your data, and 3 essentially captures all your data. Uh-oh. It's going to leave out, crumbs. It's going to leave out the outlier, the way out number, but it's going to pick up most. So at 3 standard deviations, given our standard deviation there was 70, and oh, what happened? I don't have it on my screen. Oh, there we go. I touched the button. Just a sec. Big screen. There we go. Given this standard deviation piece here, you've got 1 at this point, captures most people, most most of the data. At 2 standard deviations, I'm going to call it almost all data. And then at 3, I'm going to call it all data, because it essentially does. So that's 2. This would be a grade, or if it was grades like on that test at 3 standard deviations, this would pick up 40 to 100. So this picks up the people that get 99%, fail a little bit. It doesn't pick up the 20%. So the 3 standard deviations. So it's kind of like looking at blocks. You've got the schoolroom, here's the average, you got this many people captured, their grades are captured in there, most. And then you've got almost all, and you think about it sitting in the room, all those people sitting around, oh, look, at 2 standard deviations, we've got almost all. And at 3 standard deviations, call it everybody except for the one person that's not here. That's what it starts to do for you. So it's useful for thinking about how do we bulk things together and say, what is this about? This is really slowing down the computer. Hang on a sec. There we go. And that's what we're after, is how do we capture most of the data? How do we make sense of it? At what point is it significant? At 68% at 1 standard deviation, it is significant. So when you hear statistics and they talk about significance, well, it's because, yeah, I captured a lot of people. Polling, you hear that. So when we hear on a poll that who they think is going to win, that's what they're talking about. They give you a 90 right there. They're looking and they ask people and they load it all in. And essentially what they're saying is, well, most are here, but there's a bit of a variation. So, you know, it's kind of here. It could go a little bit either way. That's what they're saying to you. That's what stats do. So stats will give us this descriptive stuff, but they just summarize. They say, here's what's going on. Here are the numbers. Here's how many students came in the room and nodded their head. And that is descriptive statistics. Inferential is when I start to be able to take that connection and say, here's the variables that affected it. Here's the independent variable I changed to. And you can change what's independent and what's dependent. If I look at students coming in the room and nodding their head before they sit down, then I could say, what's the independent variable? Well, if they're girls, what do you see? If they're boys, how many do you see? If they're in year 1, how many are doing that? How many in year 4? So you start to look at those sort of things and say, okay, this is the independent variable. If I change this one, if I make it a different piece here I'm going to look at, is the result different or the same? Does this one affect this one? And that's what you're looking for. So you start to make statistical inferences. And we start to say, oh, here's a population thing. Here's what's going on in the population. Now, another number you're going to see is z-scores. Z-scores, and when you learn some of these, when you're doing it, you may be with Raphael Jabati. He's really good. If you are, listen to why you use it. How is it useful to you? So a z-score relies on standard deviations. What this does, so here's where the standard deviation is. You think, well, okay, I'm betting half of you are saying, who cares? But if you're going to grad school, so they ask 2 things when you apply to grad school. They ask you, what's your project? Is your project interesting? And more importantly to them, sometimes is, will you finish? Because it's a politics thing and it's budgeting. They get money to help support you through school. So the university relies on, we've got 100 grad students, or we got 1,000 grad students, and the province funds them based on that many grad students. So you pay part of your tuition, but the government pays a whole bunch more. So if you think about your tuition now, all of you that are here, you're paying about $4,000 a term. If you're an international student, you're paying about $14,000 a term, because they're paying it all. So because you live here, the government pays almost $10,000 of your $14,000 tuition. So when they're looking at you for grad school, they want to know you'll complete. Because if you go through it's a 2-year program and 1 year in you drop out, well, now they don't get funding for you for next year. They get an empty chair. So it starts to matter. So when they start to decide, do we take you or don't we, they don't look and say, they can look at your grades and say, what are your grades like? But if they're good at it, they will look at your z-score. Because your z-score says, what this does is says, how do you compare to the rest of the people in the room? If you've got a really good teacher, then maybe it works for you. or you got a teacher that just connects with you well, it works for you. If you got a crappy teacher, your grades are low, and it's not your fault, it's because of the teacher. So what this does is doesn't compare you across the board, your average in, say, research methods between 2 or 3 different profs. It says in this room with Irwin, the grades in John's room are about this, here's where the averages were, and here's where this person stood. So if you look here, and this is why it matters, if you look at your which grade is better, we typically think, oh, 81 is better. And how do we get there? So your grade was 81. But the average in the room was 62. Standard deviation of 7.5. So what they did is took 62 as the average. Remember, I did the standard deviation, most people, almost all, and everybody. So at one standard deviation, if the average grade is 62, most people's grades are between, think about it for a sec, you try it, 62 is your average. And the standard deviation, so most people's grades are between what and what? Call it 55 and 69. So it's 54.5 and 69.5, but it's within that range. That's where most people's grades are. So they look at you and they say, oh, you got 81 in your class. But the class is this, and they do this little calculation, the average divided by the standard deviation. Your z-score is 2.5. What that says is the highest you can get is 3. Remember, because one standard deviation is most students, it's 68% of your population. 2 standard deviations is 95, so almost all. And at 3 standard deviations, we're going to call it all. So the highest you can get on a z-score is 3. And the lowest you can get is 3, because you could be either side of that. They're going to look and say, wow, you got 2.5. Good, we'll take you. In grad school, they'll look at that and say, you're way above the rest of the room. The rest of the room is between 55 and 69. That's our one standard deviation. 55 here and 60. No, oh, 69 on this side. No, that didn't work. Do it this way. So that's where most people are. You're way up here. 81 puts you way above. So that's one standard deviation. So they just look at this bottom bar to say, do we take, do we don't, do we or don't we take you? And it really is kind of that simple. Let's go on to the next, because here's what else comes with z-scores. So if you look at your z-score, which is a better score, you all look at your grades. Everybody does it. We all think that you just look at your grade. What's my average? It's not as simple as your average. I look at your average, but I look at it compared to other stuff. So let's look at this class. 82 is the average, and 74 or standard deviation of 9. So you get a score of 82%, right? You think, well, I'm a great student, I got an A. But the class average is 74 and a standard deviation of 9. What's the math? What is 74 minus 9? 65. What is 74 plus 9? 81. So how significant is your 82? Whatever. You're in one standard deviation. You're kind of like in there with everybody else. There's no magic to you. So 74 plus 9 is 83, sorry. So you're not even at 1, like you don't count. You're just there. Latin, though, if they look at it and they say, no, there's other things go with it. It's what's your topic connected to and that. But in Latin, they say, oh, your grade was 67. So we would typically look at it and say, well, that's a low grade. But when you look at the average is 58 and the standard deviation, so it's not about just the class average. It's with the standard deviation becomes meaningful. The average is 58, you're 67. So, oh, good, you did well. The standard deviation is 5. That means most of the grades were lumped in close. Most of the grades were between 53 and 63. 67, where's that stand? Way up. So you could look at a 67 and say, what a crappy score. As a Z-score, like that grade's no good. I don't want to apply to grad school that. If you apply with a Z-score on that Latin, that's when they look and say, wow, okay, you're way above. If you had a crappy professor, the Z-score will make up for that because, yeah, the grades were all lower. Maybe they're really hard grader. So the grades are really low, but you were way better than everybody else. In this one, maybe you've got an easy instructor, or maybe it's just everybody gets it. Maybe it's a good instructor. You're just in the bulk. So that's what standard deviation does for us, and that's how it helps and works for in the Z-score. Does that sort of make sense? Is that useful? Like it actually turns into real things that are done in the real world. Now you start to look, and this is what is kind of interesting with casinos and stuff and large numbers, and this is what quant does for us. If you roll a die, there's 6 numbers on the die. When you roll it, the chances of a 2 coming up are 1 in 6. And the next time you roll it, it's 1 in 6. And I would say 1 in 6 every time it's 1 in 6, because I think qualitatively, it's what's it going to come up? They do math and they work out the math and say, no, if you roll 4 throws, it's actually 4 in 6. If you flip a coin, I think I did this in the beginning or near the beginning. If you flip a coin and you get heads 60 times in a row, the next time you flip it, do you think you're going to get heads or tails? Because if you're thinking heads, you're probably rolling along that line of, well, evidence shows that it's heads. So maybe there could be a bias. Could be the person that's flipping the coin there's a bias in the way they flip. So that, that sort of causes some grief. It could be that the coin's heavy, it's weighted. That would be a bias. Could be that it's a 2-headed, both sides of the coin are a head. Double-headed coin, a bias. So we call that bias in regular research, but in a coin toss, there's something with the coin. If for us, the coin toss, so every time you flip it, I think inductive. I say, well, the coin tosses, they start to work probability into it. And in that probability, you say, well, if it's been 60 already that many times, it's time that it became tails. So I'm going to bet on tails because it's time. Whereas the other side might say, no, I'm going to stay with heads because there's no right answer. In my world, it's 50-50. It never changes because every time you do it is. If you go to the casino, and what's interesting in the casino is that's where people think they can win at a casino. Well, that winning at the casino is because they will do, there's one called, what's it called? Oh, roulette. When you play roulette. So roulette, I think, has got 52 numbers on the board. There's 3 green ones or 2 green ones, but all the rest are black and red. So what they say is if you bet black and red, you stay with those ones that are the big ones on the board. If you double down every time, eventually you'll win. So you put down $2. If you lose it, then the next time you put down $4. If you lose it, you put down $8. If you lose it, you put down $16. If you lose it, you put down $32. If you lose, you put down $64. If you lose, you put down $128. And what you get in all of that is you keep putting down your money. And the odds say if you do it 7 times, by the 7th time, it will not go further than 7. The odds say you'll do it. Well, that's all very good. But the casinos all work because people work those odds. And every so often, somebody runs out of money. So they do 7 in a row. So they probably spent $300 now, or probably $220 or something. They don't have 300 and the last one they did was 8, 16, 32, 64, 128. They don't have the $256 to put down, so they can't bet again. They just lost all their money. So odds don't work. Well, they do, but they don't. Like everybody relies on them, and we often rely on them like they're some kind of science we can count on. And we need to be careful because there's the roulette one. Absolutely, it says so 36 numbers. These ones are green, and you bet on it this many times. So those casinos make a ton of money because people keep betting on them. They keep thinking the odds work. Now, when we go to the next, this is important when you think about rates versus frequency. This is the number of births. The purple one is the number of births in the provinces in Canada, and it's cancel. So when you look at this, you look at Northwest Territories, Nunavut, and say, oh, geez, they're not having hardly anybody, right? Because this is, when you look at the total number in 2005 per 1,000 births, right? There's not even 1,000 there. Now, when you look at that, you say, oh, they're in trouble. But when you look and say, oh, wait a minute, when you bring in the rates, the percentage, so the purple is frequencies, the actual number. When you bring in the rates, the percentages, you start to say, oh, their birth rate is quite high. They've got a very small population. So, and lots of them are having birth or having babies given their population. In Ontario and Quebec, all kinds of babies. But they're just kind of average in terms of where do they fit in Canada, because there's so many people living there. So if you look at research and they give you the frequency, the number, you want to ask for the rate. If they give you the rate or the percentage, you want to ask for the frequency. If I tell you, so that Milgram experiment we watched, when Milgram ran his original experiment, if he ran it with 400 people and 65% of them went all the way to pushing the button, to giving people a 450 volt shock, if 65% went, that's a pretty significant number. But the one we watched where there was 12 people and 9 of them went all the way, we said, wow, 75% of it. When they redid it in 2009, 75% of the people went all the way. Well, 75% is 9. When you ask the frequency, you say, wait a minute on that. I am not going to get carried away based on 9 people. Who are those 9 people? What biases were in there? So you start to shake it out and say, well, I'm not so sure. So there's that element of you need both. Don't get fooled into just accepting one. The one is not a good idea. Now, when we think about the deductive thinking, I want you to get your head around this. The library sample that we looked at. If you remember, this is going way back, week 3, I think. How many books are there? So I think the books now, was 86,000 something. Anybody remember? It was 86,893 or something. So call it used to be 120, but whatever that population is, what you saw or what you calculate, you don't calculate the ones that are behind. You don't know the ones that are in the locker storage or tucked away or being fixed. What do you count as books, ebooks, textbooks, Dr. Seuss books? This term becomes important to us. Who gets to define it? What does it mean? If we look at, and here's where you start to get that deductive method I talked about earlier. If premise is I took a random sample, so I decided to draw out 100 books. I went and I looked at 100 books on the shelves randomly, which I just walked down the road and said, oh, look at that one, look at that one. How did you decide what random is? The computer would do that for you. You can set a whole bunch of series of numbers up and it will generate you a random sample. Or you can go and, because if you go and walk around the library and try and do a random sample, you will probably end up with a systemic sample, because there's going to be a way that you draw that you don't even you're not aware of. The second premise is I took out 100 books, and of the 100 books that I looked at, 95 are academic books. Well, that kind of makes sense. It's in a university. And the conclusion is that 95% of the books in the library are academic. I've taken my sample, my 100, and what I saw in the sample, I've transposed it to the whole population. So I say, there it is, 95%. We see that in polling all the time, in government polling. So if you look at the last election in Ontario, they said it was pretty even between the 3 parties, and the Liberals wiped it out. And the polls were wrong, because the polls did this. They took a random sample of people in Ontario. Out of their random sample, most said 60 or 70%, it was like 30% here, 30% there. It was split pretty much 3 ways. And if they took 100 people, it was about 30 in each. And then what you got is the Liberals came through with 60%. So it didn't show up in their sample. They had the same thing with the federal election. What they missed in that is the politics of, they did this random sample, but in their random sample, what they missed is how many people go out and vote that didn't vote before, because Obama had this. In the US, they had a whole bunch of people that went out to vote because they never bothered before. It wasn't worth it because the system didn't reflect their interests. So now they went to vote. And so the polls run because, wow, what happened? All these people went to vote because they think we need to go and bring change. It's time to bring change. So now they connect with it. The poll doesn't capture that kind of politics quite the same way. So the poll does just this, exactly the same. It's a premise. The premise is a random sample. The premise 2 is how much of that sample went one way or the other. And then my conclusion is I take it from the sample to the population. That's statistical conclusions. If you look at, so that's the election that I just talked about. And they talked about confidence interval, which says, well, you know what, and this is where it's kind of, I find this funny, because they tell you that this is what it is within 4%. So that means mostly we're right, but we could be wrong. And this is why the company that did those 2 polls for the provincial and federal election are still in business, is because they said, wow, like that's that odd one, right? It lets them say that it's not a big deal. It just is. So at the end of the day, that's where you sort of look at stats and say, so why do we hang our hat on it? Statistics make us feel comfortable. If you say, well, because most of my friends are, and I hear it lots, right? Well, most people do this. Most professors do this. Or we very much go to that statistical place of most, and we feel comfortable with it. So if we don't, if we let it go, then if you don't hang your hat on stats, then you sort of say, what's it about? Why does it matter? Why doesn't it matter? So it's not that one is better than the other. Qualitative is looking at the very individualized sense of what's going on. You're up close and you want to really get a sense of it. Quantitative gives you this broad sense. They're not better or worse, they just weigh out differently. So deductive arguments, I make a conclusion and it could be wrong. So the election poll was the same as the academic one there. It was this thing in elections they did, but their deduction was wrong. We like to think it leans us towards thinking it, but didn't work out. That leads us to inductive. So inductive says, oh, so the premise, conclusion didn't work. So let's look at the odds. And the odds of it working are, so the odds is gambling. The odds goes back to what I did earlier there. It is the odds of large numbers. It is the roulette wheel, the roll of the dice. They are probability theories, inductive odds. So that's where it starts to matter. The randomness, random is really random, and it's not very often we see it. But people have all sorts of things that go with random because they think these sorts of things with them. So the last piece on stats, unless you have some questions for me, is this. When you think about what a stat is. Right? We're not eating one meal. Like we're not eating in one day, once every 6 days. Stalin, particularly nasty person. Some say he was a big part of saving World War II because he was the Russian premier. He starved them out as the Germans went east. So, but he was a very mean-spirited dictator. So and that's what he said. If somebody in your family dies, you're going to cry. Everybody at war, and we think about terrorism and all those things and wars and stuff, every mother cries regardless of what side they're on. If their child dies, they cry because it's a tragedy. I've lost this. Statistic, it's kind of whatever. How many people died? Not very many. Oh, well, then we don't have to worry about it. So if you think about this, and here's one for us, we think about, so as a statistic, and here's where we get into stuff. I'm sure you've seen video or TV stuff or whatever. How many kids do you think died this last month in Africa because they didn't have fresh water? How many do you think got a disease because they didn't have clean water? The thing with the statistics, so when it's far away, it may not be up close to us because, well, it's far away. So we hear, oh my goodness, there was, 10,000 children died. So the statistic doesn't always mean it doesn't count. We might look at that statistic and say, holy crap, that's a lot of kids. We need to rally together to change this. We need this to stop. That statistic, because there are lots, helps. But if it was only 10, those 10 mothers still cried. And is there a difference? I'm not sure there is. when it comes to, and there's qualitative. It doesn't matter whether it's 1 or 100,000. If that child died of starvation, we should be thinking about trying to prevent that. We didn't want that to happen. So that's qualitative. They go together. One's not better than the other. They fit in different ways together. So, and that's kind of my view of the two. Does that help and make sense? Is it useful? Any questions? You're exiting now. Good, we're out. So that's it. Course is over. I hope you get the test done or get her done, and I will see you soon, Bianca. I think I got your email. You've got my response, I hope. And